Hi everyone and welcome to the Support Vector Regression or SVR Intuition Lecture. SVR can be a bit of a challenge to clearly examine it without taking in a range of context, but we're going to take a look at it in a relatively simple term to condense the information. As you progress into the hands-on part after this lecture and to the Support Vector Machine section later on in this course, it will help reinforce some of the information that we are going to discuss. So what is SVR? What can it support? Since you have seen linear regression, SVR has parallels, but also does things a bit different. SVR is a type of support vector machine that supports linear and nonlinear regression. So how can we look at that? If you imagine a street for our example, instead of trying to fit the largest possible street between two classes while limiting margin violations, SVR tries to fit as many instances as possible on the street while limiting margin violations. Also, the width of the street is controlled by a hyperparameter referred to as epsilon. And we're going to take a look at a visualization in a moment to help reinforce that. But just keep it in mind for now and let's delve a bit further. SVR performs linear regression in a higher dimensional space. What does that mean? Try to think of it as if each data point in the training represents its own dimension. When you evaluate the kernel between a test point and a point in the training set, the resulting value gives you the coordinate of your test point in that dimension. The vector we get when we evaluate the test point for all points in the training set, the k vector, is the representation of the test point in the higher dimensional space. And once you have that vector, you then use it to perform a linear regression. And if we take a look at the following visualization, we can see what we referenced earlier. We are trying to fit as many instances as possible on the street while limiting margin violations. So you have, for our example, our street, and we are trying to limit those violations. We have our epsilon parameter that controls the width of the street, and also our support vectors, or the points within the street. And you could really see from this visualization what support vector regression is performing. Again, there are parallels and similarities between linear regression, since we are performing support vector regression, but the point is to limit the margins with epsilon and to find the support vectors within the street. And on a side note, SVR, and in particular Gaussian processes, are a very good method to use for efficient computations by pre-computing a training set and then using SVR to interpolate the results. Let's take a look at the requirements for SVR. SVR requires the following training set, which covers the domain of interest and is accompanied by solutions on that domain. The work of the SVM is to approximate the function we used to generate the training set, to reinforce some of the information we've already discussed. In a classification problem, the vectors x are used to define a hyperplane that separates the two different classes in your solution. These vectors are used to perform linear regression. The vectors closest to the test points are referred to as support vectors. We can evaluate our function anywhere, so any vectors could be closest to our test evaluation location. While we are working through this, and again, some of this information might be a little bit repetitive, but try to use the diagram that we looked at before, since it's an accurate representation of this information, and we're dealing with our example of the street. Use this as a reference. Again, it's containing our support vectors, our epsilon parameter, and its intention to limit that space. We aren't performing that direct linear regression, but we want to limit that space and have the support vectors within. Let's continue. So how does SVR work? Or what steps are necessary to perform SVR? And we're going to get to the main part of the algorithm in a moment. But first, we need our training set as the first step. After that, we have to choose a kernel and regularization. We then have to form the correlation matrix. For the fourth step, you now have to train the machine to obtain the contraction coefficients. And then you can use those coefficients to create your estimator. So you now have covered a decent amount of information, but stick with me because we have a little more to go. For our next step is to choose a kernel. One of the prominent kernels for SVR is the Gaussian kernel. Kernel choice becomes important because if you choose a kernel that goes to 0 as the distance between the arguments grow, as you move away from the training data, the machine will return the mean value of the training data. In addition to choosing a kernel, regularization also is important, and it matters because due to the training sets with noise, the regularizer will help prevent wild fluctuations between data points by smoothing out the prior. And try to keep all these details in mind, so when you start working on it in the next lecture, in the hands-on part, it may help reinforce this information to sink in further. We are almost there, but we have to examine the main part of the algorithm now coming up. And then we'll do a recap to wrap it up, an overview, so we can digest some of these terms and information a little easier. We are now arriving to our correlation matrix. And mainly you are evaluating your kernel here for all pairs of points in the training set and adding the regularizer resulting in the matrix. Then we have the main part of the algorithm. The y vector of values corresponding to your training set, the correlation matrix, and then the unknown or set of unknown we need to solve for. In order to solve it, we have a pretty simple process, which is inverting the matrix here and applying it to the vector y, which you have right in this example. Once the a vector parameters are known, you can form the estimator. We then use the coefficients we found during the optimization step and the kernel we started off with to estimate the value for y for a test point to compute the correlation vector of k. Also, to find the inner product with the alpha vector. Finally, we compute the element of k as the following. Overall, we have to form the correlation matrix, then solve the matrix to form the estimator, and form the estimator for the support vector regression as the main steps of the algorithm. Alright, the intuition behind SVR can seem a bit challenging, but to recap, let's try to simplify it a bit further. SVR has a different regressional goal compared to linear regression. In linear regression, we are trying to minimize the error between the prediction and data. In SVR, our goal is to make sure that the errors do not exceed the threshold. What SVR does in this sense is that it classifies all of the linear predictions into two types: the predictor lines that pass through error bars drawn and predictor lines that don't. The lines that don't pass through those bars are not acceptable because it means the difference or the distance between the predictions and the actual values at those points have exceeded the error threshold. And for one more time, we've seen the following visualization before, but it shows the clearest intention of SVR. What the algorithm is concerned with is controlling the threshold and support vectors within it. It's not exactly the normal form of linear regression as we can see, but to use the term threshold or epsilon, what's going on between the established points. As you move into the practical lesson, along with the SVM section later on in the course, it will become evidently more clear, as SVR in a sense is an extension of an SVM. But as always, if you have any questions, please feel free to share them. Enjoy the practical exercise with SVR and enjoy machine learning.